The previous subsection dealt with the case where we knew the analytic definition of the function that we were trying to find the Fourier series expansion for. So if we were given an x of t, and for any value of t, we could determine the value of x. But now we'll deal with the case where we don't have an analytic description of our function we want to expand, but we have discrete data points. And something like this would occur if we are collecting data on a real-world system. We are only knowing the value of our x of t at very specific values of t. So what we're going to address now is the discrete Fourier series or discrete Fourier transform when we have this as our case. So we have empirical data where we have measurements of the data and specific timestamps, but we don't know that underlying generating function that makes the x of t in general. So we run into some problems here compared to the case where we have the analytic function, is that now we're going to be limited in how detailed a series expansion we can do, the resolution of it, which means the spacing between the frequencies that we can determine, and also the overall range of frequencies that we can expand into is going to be limited by, one, how much data were collected, and how quickly the data were collected. So the sampling frequency is how quick it was collected, and then more or less the time span or the number of data points that we have collected. One thing we're going to be able to do, looking a little bit ahead, is with a discrete Fourier series, or where we have this data collection, we're going to be able to do the discrete Fourier transform, the DFT on it, and one use of that is going to be to use the coefficients in order to generate the power spectral density, which is going to be telling us the relative strength or the absolute strength of each frequency's contribution to our original signal. So we'll get into more detail in that in a little bit after we look at the process for doing a DFT. So I want to again emphasize here for the discrete case, when we're collecting the empirical data, we're going to be limited by how long we collect the data. So the longer we collect data, or really the more samples that we take, is going to increase the resolution for our discrete Fourier transform, as we'll see in the example. So the spacing between frequencies we can detect is going to get smaller the longer we sample. So in general, sampling longer is going to be better and will increase that frequency resolution. Again, the other limiting case is how quickly we sample. So the faster we sample, the higher the maximum ranges of the frequencies we are able to detect. So all things considered, the longer we can sample, the faster we can sample, the better, although there are going to be drawbacks. Sometimes faster sampling is going to give us noisier data, and if we sample very long or collect a lot of data points, being able to store that or buffer that might be an issue. So now let's say we collected our data, we know how long we sampled it for because we have all the timestamps. We know the sampling frequency because, again, we can see the timestamps and the spacing between them. So now how are we going to use this? Once we do, what's the type of data we're going to be able to look at here? Well, the technique I'm going to discuss for doing the DFT on this data is specifically good only for stationary signals. So again, what we're looking at when we're talking about vibrations is typically periodic functions. Now, when we had the analytic definition previously, we saw that that same small pattern repeated over and over and over again in our signal infinitely. And what we were looking for was kind of what's the smallest repeating pattern. Let's analyze that, and then it can generalize out. Well, in the real world, with real signals, this is not necessarily going to be the case. That one, when we sample our data, there's going to be some noise to it, so every repeating pattern might look a little bit different. And also real world things we measure might not exactly repeat themselves over and over again. So an assumption or a condition we're going to have when we're doing the discrete Fourier transform is that our signals are stationary. So that is to say that in time, they are going to repeat themselves over and over and over again. It's not going to change over time what that signal is doing. Now, again, this is an assumption because no real world object that we study is going to be exactly stationary. But it's an assumption that we're going to make that kind of on average, it's doing the same thing over and over again. If we have non-stationary signals, so these are going to be ones that over time that pattern is going to change, discrete Fourier series or transform is not appropriate. Because as we'll see with the equations, the DFT is doing more or less an averaging. So if we are changing over time, we don't want to be doing the averaging over time because it's changing over time, so the average isn't going to tell us much. So if we have a signal that is repeating but changing over time, maybe slowly, maybe more quickly, the DFT is not what we want to use. We want to use a different technique, possibly wavelets would be the answer to this. I won't get into that in this class, but wavelets are kind of a generalization of the discrete Fourier transform that now allows things to change over time, and we can still study the frequency content. But we're going to assume or limit our scope to stationary signals in this class. The other assumption for this DFT technique is going to be that our data were sampled uniformly. Whatever that sampling rate was constant. Now again, this is not always the case when we are taking real-world data because it might depend on our data acquisition device. If we're using something like a DAC box, that's going to be able to take a very uniform sampling, and really every sample we take is going to be uniformly spaced in time. But if we're using a different type of data acquisition device, possibly like an Arduino, it's going to more or less take our samples with a constant rate, but sometimes it'll be a little faster, a little bit slower. It depends if its buffer fills up or if it has to send the data over to the computer or things like that. So it's not exactly uniform in this case. So a DFT is not going to work on the data, at least as we collect it, off of something like an Arduino. Now, there are again ways to remedy this or compensate for this. So one, we could take our data that is not uniformly sampled, but if we have all the timestamps and we have all the signals, we could, in theory, resample it using something like a linear interpolation. Now, this is changing the data a little bit. We're making some assumptions. We're smoothing the data a little bit if we're doing an interpolation. So if we interpolate the data into a uniform series, then we've lost a little bit, we've smoothed it out too much, so it's not exactly the signal that we collected. But we can probably get a pretty good idea of the frequency content still. Or there are other DFT techniques that don't rely on uniformly sampled data that you might be able to employ. And finally, the method I'm going to be presenting here is going to be kind of a very manual, slow method for determining what the coefficients, those A's and B's we were talking about in the previous subsection were, but on our discrete data. There are certainly more efficient ways to do this, but this is going to be using kind of the very definitions of the Fourier series expansion for our coefficients. More commonly, you would use a fast Fourier transform or a discrete fast Fourier transform to do this. There's a lot of tools built into MATLAB or whatever program you're using to do your signal processing that are going to find these coefficients much more efficiently. And that's where an FFT routine is going to be useful. We're also going to look at, when we get into power spectral density, using something called p-Welch in MATLAB, which is again going to be a more advanced method for finding these coefficients and then plotting them in a power spectral density. All right, so what is the basic method we want to use to do a discrete Fourier transform or do the discrete Fourier series expansion? Well, we're not talking about continuous signals. We're talking about these discrete signals now. So in the continuous case, we could completely reconstruct a signal or construct a signal out of an infinite number of sines and cosines, but there had to be an infinite number of them. And if we knew all the coefficients, we could, with 100% accuracy, recreate our signal. But now, if our signal is x, we can use this expansion formula that uses the summation, but it's not an infinite summation. It is going to be limited because we can only find so many coefficients based on how long we were sampling our data. So we cannot 100% reconstruct the original signal because we can't take an infinite number of terms in this summation. And the other thing to note is we can only reconstruct our signal at specific times. So the t's are now going to be discrete values. We can't just plug any t we want in there. All right, so we still have the coefficients like we had in the analytic case. We need our a naught term, we need all of our an's, the coefficient in front of the cosine terms, and all of the bn's, the coefficients in front of the sine terms. So how do we determine these coefficients? It's actually going to look really similar to what we were seeing when we were doing the analytic case. So the A naught is going to be 2 over n. So that's similar to what we saw before. It was 2 over the time span of that smallest repeating signal, multiplied by the summation from 1 to n of the signal that we collected. So those discrete signals or samples that we collected. So on this slide, I'm going to be using capital N as the number of samples that we took of our signal. So what we see here is we add up all of the samples we collected, we divide by n, and then we multiply by 2. So really what A naught is twice the average value of our sample. With that A naught term out of the way, now we can start looking at our AN terms and the BN terms. So again, like we saw for the analytic case, we're going to have one of these A values and B values for every value of little n. And we see that constructing them is going to be pretty similar to what we did for the analytic case. We take the value of the signal of the ith timestamp, or the ith signal that we took, multiplied by the cosine of 2n pi over t times ti. Now, we want to be cautious here of the difference between that fundamental frequency we found in the analytic case versus how we're using our omega or our fundamental frequency in this discrete case. So I advise that you take in the analytic case to take that smallest repeating pattern. That is your capital T, that's your period. And then the fundamental frequency would be 2 pi over that T. But in the discrete case, it's going to be different because we are going to use our entire time series, all of the data collected, to determine the value of T. So T is the entire length of time that we were sampling data. And then our fundamental frequency, our omega, is going to be based on this value of T, still using that 2 pi over T. So this is where the resolution is going to come into play, and how the resolution, or the spacing between frequencies we can detect, is dependent on how long we sampled our data. So if omega is 2 pi over T, the larger T is, the smaller omega is. And what we're going to be doing, if we look at that top equation, since we're taking omega and then 2 omega, 3 omega, the smaller that initial value of omega is, the smaller the difference between all of those omegas is going to be. All right, so for the AN, we're taking our signal times the cosine of this term, and for the BN, we're taking the signal at each timestamp I times the sine of 2n pi over t times ti. Right, so where we want to be cautious here when we are doing these summations, notice that the summation term for AN and BN is over time, or over the number of samples we have. We have capital N samples that we took. But what we're looking for is if we want A1, that little n value, that's only appearing inside the cosine term or inside the sine term. So for every little n value, are we talking about A1 or A2 or A3? Well, we're going to find it the same way. The only difference is what is the little value of n inside the trig term. So we'll apply these equations in the next example so that we can find our whole list of AN and BN terms for a discrete signal.